Dear students, we shall discuss on chemical kinetics. Now, chemical kinetics is an important aspect in chemistry. By carrying out chemical kinetic studies, we can approach or we can arrive at the mechanism of a reaction, the conditions required for a reaction. We can optimize a reaction, any type of reaction, be it organic, inorganic, etc. A lot of information we get by carrying out chemical kinetic studies. Now let us see what chemical kinetics is and what are the aspects which we deal in chemical kinetics. Now, chemical kinetics is nothing but a study of the rate of a reaction. That is, how fast a reaction happens, what is the speed of a reaction, is studied under chemical kinetics. Now, there are different types of reaction depending upon its speed, like slow reaction, very fast reaction, and moderate reaction. Reaction with moderate speed. Now, when we talk about slow reactions like rusting of iron, then certain radioactive reactions, etc., quite slow that it takes a lot of time to complete the reaction. Okay, there are fast reactions which happens within a fraction of seconds. Now these two reactions, that is slow reactions and fast reactions, their kinetics, the study of the kinetics of such reaction is not worthwhile. Like slow reactions, there is no meaning in studying the rate of that reaction. And fast reactions, it's not possible for us to study the rate of a reaction because it happens within a fraction of time. While the reaction with moderate speed, we can carry out study the kinetics of such reactions. And using this reaction, that is reaction with moderate speed, we can study the various principles of chemical kinetics. To study the various principles of chemical kinetics, we depend upon the moderate speed reactions with moderate speed. So, the rate of a reaction or the reaction rate can be defined as the measure of increase in the concentration of products or decrease in the concentration of reactants per unit time. Or we can say that it is nothing but the study of or the measure of change in concentration of reactant or product. Alright, so that is study of change. Reaction rate is the change in concentration of reactants or products per unit time. Okay, so the change in concentration of reactant or product with respect to time is the reaction rate. That is the definition for reaction rate. Now, the unit of reaction rate of a reaction is moles per liter per second if it is in the liquid state, and if the reaction is in the gaseous state, then it will be in atmosphere per second. So these are the units of rate of reaction. That is moles per liter per second, concentration per unit time, and here pressure per unit time in the case of gaseous reactants or gaseous reactions. Alright, now let us take an example, just a general example wherein a reactant A gets converted to product P. Okay, this is a general reaction. Now what happens? How can we express the decrease in the concentration of A? Now as time passes, we know that the concentration of A decreases and the concentration of P increases. Initially, in the reaction pot, the concentration of A will be 100% and concentration of P will be 0. But as time proceeds, as the reaction starts and it proceeds, what happens? Slowly, the amount of the reactant A comes down and the amount of the product P goes up. So the rate of decrease in the concentration of A can be expressed as minus delta concentration of A by delta T. What is minus for? Because it is decrease in the concentration. When you subtract the final concentration from the initial concentration, we'll get a negative value. And delta T is the time difference in which you are measuring the change in concentration. Similarly, the rate of increase in the concentration of B can be expressed as delta B by delta T. Here we do not have a negative sign because the change in concentration of B, that is, it is a positive value, it will be increasing. Alright, so this is the way we express the change in concentration of A, rate of change in concentration of A or rate of change in concentration of B. So the average rate of a reaction can be put as either the change in concentration of A or the change in concentration of B. So the average rate of a reaction, R average, is equal to either minus delta A by delta T or plus delta B by delta T. See, there is an equal to sign here. It can be either with respect to, you can talk about the rate of reaction which was either with respect to A or with respect to B. Either with respect to decrease in reactant or with respect to increase in the product, concentration of the product. Okay, so one more thing which you have to keep in your mind is that the average rate of a reaction is measured over a long time interval. Okay, it's not short time interval which you measure. The average rate of reaction is measured over a long time interval. Say between 5 minutes to 10 minutes, like that, after the reaction starts. So you take a long time interval to determine the average rate of a reaction. Now, let us see how the rate of a reaction or the change in concentration of the reactant and the product is can be plotted in a graph. Now, suppose you are going to plot a graph with x-axis and y-axis. On the x-axis, you plot the time, you mark the time, and on the y-axis, you mark the concentration. Then, this particular, the change in concentration of the product B will be in this pattern. Initially, there will be a sudden increase in the concentration, and as time passes, the change in concentration or the increase in concentration of B slowly comes to a constant or straight line. Now initially the large increase is because initially the reaction will be at a faster rate. But as time proceeds, the reaction will be at a slower rate. So at a particular, the total rate of the reaction will be the rate of at each time. Okay, at each instant of time. So this will be the pattern of plot of increase in the concentration of the product B. Similarly, if we plot a graph in terms of concentration of reactant A, then it will be in this way. The concentration decreases. See, initially there will be a sudden decrease, and then slowly the change in concentration is not much. The decrease is very slow. Alright. So, now if you want to know the change in concentration of either A or B, take the slope of this plot, draw a tangent and take the slope of this plot, you get delta A by delta T. Okay, so this is a large time interval which you are taking from this time to this time. So that will be the average rate of a reaction. Now, let us take an example, that is formation of ammonia. N2 plus 3H2 giving 2NH3. This reaction completely is taking place in the gaseous state. Now, you can see here, for every mole of nitrogen used, 3 moles of hydrogen is used and 2 moles of nitrogen is formed. So for every mole of, ammonia is formed. So for every mole of nitrogen used, 2 moles of ammonia is formed. For every mole of nitrogen used, 3 moles of hydrogen is used. So in terms of rate of reaction or the change in concentration, for every mole of nitrogen lost, 3 moles of hydrogen is also lost. And 2 moles of ammonia is formed. Okay, so here we have to consider the stoichiometry of the reaction also. In the earlier case, A giving P, both A and P, the stoichiometry, the number of moles of A, number of moles of P formed is the same, but here it's different. So while writing the average rate, we have to consider the stoichiometry of the reaction also. So accordingly, we will be writing the rate of the reaction, average rate of the reaction in this way. So here you can see we have divided the change in concentration of change in concentration with respect to time with the stoichiometric coefficients. So see here we have taken minus 1 by 1 for when we are discussing or considering the average rate with respect to change in nitrogen. Okay, now here we are dividing it by 3 because 3 moles of hydrogen is used up. Here we are dividing it by 2 because 2 moles of ammonia is formed. That's a stoichiometric coefficients. 1, 3 and 2 are the stoichiometric coefficients. Okay, so from this it is quite clear. For every mole of nitrogen used, 2 moles of ammonia is formed. Okay, or you can say that for every mole of nitrogen used, the amount of ammonia formed is twice that of the amount of nitrogen used. The amount of hydrogen used is thrice that of the nitrogen used, and so on and so forth. So for a general reaction, AA plus BB plus CC plus DD, giving CC plus DD, the average rate of a reaction will be written like this. Okay, minus 1 by A by delta T is equal to, or with respect to B, we can write it as minus 1 by B delta B by delta T. With respect to the product C and D, you can put it with respect to C plus 1 by C delta C by delta T plus 1 with respect to D plus 1 by D by delta T. So the average rate can be written either in terms of A or in terms of B or in terms of C or in terms of D. Okay, so this particular aspect you have to remember. That means you can monitor the change of concentration of any of these components, that is any of the reactants or any of the products, and then determine the rate of a reaction. That's important, and that's the beauty of this kinetics. You take any one component and then study its change in concentration, monitor its concentration change. So in a reaction, there may be a colored compound which has been formed. You can monitor the change in concentration of that colored compound. Okay, or there will be a base form, so you can carry out and monitor the reaction or monitor the rate of the reaction by measuring the concentration of that base form, and so on. So when we'll be discussing how do we measure or determine the rate of the reaction. So that's it. So average rate can be easily determined by monitoring the change in concentration of any one of the components of the reaction, any one of the reactants or any one of the products. Now, the average rate, as I said earlier, does not give us the rate of a reaction at a particular instant. It gives us the rate of a reaction over a long range of time, isn't it? Long period of time. And when we have seen the plot also, let us go to the plot once more, because I do not know where. So in this plot, what do we find? The change in concentration is not uniform throughout, isn't it? Initially, there will be a large increase, and then as the time proceeds, the change in concentration is lesser, or becoming almost constant, isn't it? So that particular aspect, so that means when the reaction proceeds, the rate of the reaction will not be the same throughout. Okay, initially the rate will be fast, and towards the end the rate of the reaction will be slow. So we have to be, that's why we consider the average rate of a reaction. Now, but the problem with the average rate of a reaction is that gives us the rate of a reaction over a long range of time. If we want to determine the the rate of a reaction at a particular instant, or in general, what will be the rate of the reaction? For that, we need to bring down the time duration. Okay, so the time interval chosen must be infinitesimally small to express the rate of a reaction accurately, the exact rate of a reaction. And hence, we bring in the term instantaneous rate of a reaction. That means the rate of a reaction at a particular instant. That is called the instantaneous rate of reaction, or RINST. So here we'll have to change the terms. Until now we have been discussing the rate change in concentration in terms of delta A by delta T. But now we have limiting it as the delta T, the change in time tends to 0. That's the instantaneous time. Then our term will change to minus dA by dt. So we introduce this particular term for the rate of a reaction. So that will be the instantaneous rate of a reaction, and our expression will change to, for this reaction, for AA plus BB giving CC plus DD, the instantaneous rate of a reaction will be minus 1 by AD, concentration of A by dt. So wherever you have put delta, you put in D in the rate reaction. So this is the same as a rate expression for rate of a reaction also. Alright. Now, so for ammonia, in the case of formation of ammonia, we can write the rate of instantaneous rate of a reaction, or the rate of reaction, as minus 1 by 1 dN2 by dt equal to minus 1 by 3 d concentration of hydrogen by dt equal to plus 1 by 2 d concentration of ammonia by dt. So this is the change in concentration at a particular at infinitesimally small interval of time. Alright. Now, how do we determine the rate of reaction rate? As we said earlier, it is by monitoring the concentration of reactant or product as the reaction proceeds, okay, at a regular interval of time. You can take up titrometry to monitor, spectrophotometry to monitor, or conductometry, potentiometry, any type of measuring technique you can use. In titrometry, you will be carrying out titration. Spectrophotometry, you will be measuring the change in or monitoring with respect to change in color. In conductometry, change in conductance, that will give us the concentration of ions, and so on. So you can use any methods of determination of the concentration of the product or the reactant, and then we can, using that particular value, we will be plotting a graph, and then let us look at how we can monitor the change in concentration of a reactant or a product with time, or how are we going to plot the graph to determine the rate of a reaction. Now you have the x-axis and the y-axis. In x-axis you mark the time, in the y-axis you mark the concentration if you are carrying out the determination of concentration. If you are determining the optical density, you can put it as that, and so on. Okay. Now you are going to monitor the change in concentration of the reactant here. So the reactant concentration is coming down, decreasing. Right? Initially there is a drastic change, decrease, then slowly the decrease almost flattens. Okay. Now, say for example, suppose your reactant is the acid. Okay. Now, what do? Initially, you determine the concentration of acid by titrating it with a base with a known concentration. Now, at every time interval, you take up 2 ml of the alicot, that is a reaction mixture from the reaction pot. Determine the concentration of the acid. Okay. So, say for every 5 minutes, you carry out this procedure. So, first 5 minutes, you take up the alicot, 2 ml of the reaction mixture from the reaction pot, titrate it against the known base. Okay. Mark the concentration. After another 5 minutes, that is at time, when time is 10 minutes or 10 seconds or 10 minutes, repeat the experiment. Okay, then 15 minutes, 20 minutes, and so on and so forth. So you will get a plot like this. Now, suppose you want to determine the rate of this reaction. Okay, now what do? Say, you just take up a point, that is, you're going to determine the rate of the reaction at this particular time. Okay, now what do? You draw a tangent to this point. Okay, and then determine the slope of that. Okay, so this will be the dA and this will be the dt. Okay, with this time interval dt. Okay, infinitesimally small. You take the slope. Okay, so the instantaneous rate of this particular at this particular point will be minus dA by dt. That is the slope of this tangent. Now, that's how you plot the graph and then determine the rate of the reaction graphically. First, you carry out the titration and then graphically determine the slope or rate of the reaction. So, using titrimetric method of spectrophotometric method or conductometric method, you are determining the change in concentration. And from that values, you are graphically determining the rate of the reaction. Alright. So now we need to discuss more about the kinetic aspects. That is, what are the factors which on which the rate of reaction depends, etc., etc. We'll be discussing it in the late coming videos. Alright. Thank you for watching. If you have any clarifications to be done, please feel free to ask. Thank you.